in the background. All right, it's 2 hours UTC, and it's time again for Astronomy Daily Live. So, hey, everybody, welcome, welcome. Come on in, grab your favorite consumable of choice, gather around, stretch those bones, and get on over here. Join the ever-growing circle of friends that come together every day, practically every single day, um, and just share a passion. Share a passion for the science of astronomy, and talking about the universe and space, and what's new, what's old. There's so much. There's so much, and the science of astronomy is I dare say, the oldest of sciences. So it's great. There's lots to talk about in terms. I've got a little friend back there. Hello. Um, uh, Great to talk about the history of astronomy and modern astronomy, the whole thing. So, yeah. So, hey there, Tom. Nice to see you in the chat. Atta is there. Mother Nature, nice to see you in the chat. Welcome, welcome. Yeah, we met over on DC 420 LA, if I remember right. So yeah, nice to see you here. Bob Dog, hey, hope everything is okay up there in the Great White North. So cheers. I've got uh, the pretty normal around here, HOH, the hydrogen hydroxide here. So cheers. So come on in, everybody. We're going to talk astronomy. And back on the panel tonight is Bobby. Hey, Bobby, what's going on?
Hey, sorry I wasn't here yesterday, but as you may know, it was a great event.
Cool. Now this is the WWE. Is that right? Is that what you said?
Yeah, that's correct. Whiskey Echo.
Cool. So it was just like a pay-per-view thing that
Uh,
you.
yes, it was a pay-per-view.
Cool. Hey there, Patrick Manny. Nice to see you also. So come on in, friends. We're going to talk all things astronomical here for, just about an hour or so. I like to, spend the first few minutes just saying hi to everybody, and yeah, just making sure everything is going. 9-inch colas. Hey, nice to see you there too. I'm gonna get my stream going over on my smartphone, so I can monitor all activities that way, just to make sure that the live stream is still going. So cheers. Come on in.
What
So
did you show yesterday on Rabbit?
you know what? I didn't do it yesterday, and I think what I'm going to have to do is I'm going to have to change the date and the time. The date and the time. I might have to change it to Sundays at 0 hours UTC. So yeah, I
Mighty
might.
KBC.
What's that?
That's going to conflict with the Mighty KBC.
Oh, is it? Okay, well, so be it. It's you know, this is a big universe. So I'm not too worried about that. And yeah, I sort of consider that um, sort of um, possibly a smaller crowd. So yeah, I don't expect a huge theater or anything there, but um, if a few friends come in, it's very, very cool. Very cool. So let's see. Uh, yes, yes, 9 inch. That is a Roland Phantom X8. That is my one of my babies, and there's another baby sitting on top of it there. So
Mhm.
yeah, yeah, that's a incredible, incredible instrument. Everything that I have asked it to do, it it has stepped up and been like very, very cool. The only problem is there only one. Yeah, actually, there's two problems with this board, right? The first problem is the weight. Is the weight. They they decided to make these keys um, feel realistic, right? So they wanted to make it feel like a piano, and I guess the only way to do that is to make it really, really heavy. So this board weighs about 60 pounds. Okay, it's insane. It's just absolutely insane. And yes, the cats do play ambient music. Uh, Actually, uh, usually better than I do. They really have a knack for the ambient. Now I have to help them a little bit in setting up the sound, right? But once the sound is is there, she'll take over and make the most amazing sounds. And I've actually done that. I've actually recorded uh, um, sounds that they've made, and I've used that as sort of a basis for songs, for compositions, and yeah. So they play an important role. Um, so yeah, right now in terms of music, um, I'm playing with a native flute player, and we're starting to get more and more gigs. We've been doing maybe one show a month or so, and that's starting to get a little bit more now too. Now it's all local. He's going to be going up to Colorado for a show there in another month. I'm not going to be able to make that one, which really sucks. Um, and then in I think it's November, we're going to Laughlin to do a show there, and then we have a couple other shows locally here in southern Arizona. So yeah, it's
You might have Steve Roach's touch real soon.
oh man, doing a collaboration with Steve Roach would be absolutely amazing. But at this point, um, you know, uh, he would hear my stuff and be like, "Nice try."
Oh Lord.
So yeah. Steve Roach, he lives in Tucson, which is only about an hour west of me or so. So cheers. I'm trying to keep up with the chat.
Yeah, Arthur Water was telling the chat admitting that she's going to try to be an orc.
Well, uh, do it while you can, Atta, because you never know. You
Now
never
I
know.
wonder if she's going to make it out of wood or make it out of metal.
Well, anything that floats, right? So yeah, you can sort of go either way. Either way. So Mother Nature, I'm in southeastern um, um, southeastern Arizona, right in the middle of nowhere, where uh, actually the most important thing here to me is that it is dark. It's dark. Being an astronomer, I want it. I want it dark. So it is very very dark here. I don't have to go anywhere to do the observations that I do. I can just walk right outside and do them. I sort of grab that scope there, and I've got a CCD camera, scientific grade CCD camera, and off I go. And I talk about my work here once in a while. I don't want to necessarily bore anybody with that, so I try not to talk about it too much. But anyway, I just saw a tweet. I'm going to share my screen here.
Now, when is monsoon season supposed to be over and done?
Monsoon season is typically finished by about mid-September. So we have at least another good month. And it was actually it usually starts. I'm going to go ahead and share my screen. It usually starts around the 4th of July, and as I said, goes to about mid-September, first part of October or so. But this year, it started really, really late. I mean, all of July and at least the first weekish or so of August was just like super, super, super dry. And it's just within the past maybe week or two that we've had sort of the typical, build up in the afternoon, rain, um, uh, in late afternoon and evening. So yeah, who knows what it's actually going to do? But check this out. I guess they've confirmed, right? Confirmed that ice, actual water ice, right? Uh, they have found this on the moon, and it seems to be situated at the poles, right? So it's kind of hard. Let's see if I'm seeing these circles of latitude here. I'm not quite sure what latitudes those are. I'm hoping. Usually, what I do uh, uh, is when I find some kind of media article or press release like this is from JPL. Usually, they have a link to an actual paper, and so I sort of skim these. But if I see an actual paper, then I'm like, I want that. But I'm not seeing anything. Um, this it looks like it's an Indian spacecraft that was either at the moon or is at the moon right now. I think, right? This is yeah, ISRO, yeah. Um, was uniquely equipped to confirm the presence of solid ice on the moon. So that's pretty cool. That's pretty cool. Now, this ice has to live. It has to exist in places on the moon where it's not going to um, see the sun, right? Because if the sun is shining on it, then it's going to vaporize, right? It has to stay in a solid form. So as you can sort of see, I guess they've sort of marked the location of this ice in blue. And let's see which is which. Here's the South Pole on the left and the North Pole on the right. And this is a pretty small region of the moon. This is not like the southern half of the moon. That's what I was saying. These rings of latitude, um, yeah, this is definitely not the southern half. My guess is that maybe this is like 5 degrees south, 10 degrees south, or maybe 10 and 20 degrees south, and then 10, 20 degrees north. Does it say? Blue represents the ice locations plotted over an image of the lunar surface where the grayscale corresponds to surface temperature. Okay, so this grayscale actually isn't light; it's actually temperature, right? So as you can see, where it's dark, it's cold, and where it's bright, it's warm. So these guys like to live in little clumps. It looks like in much of the dark regions. Not all of them, right? Not all of them, but in some of them. The ice is concentrated at the darkest and coldest locations, right? Definitive evidence, they say. Definitive evidence. So that's pretty cool. That's pretty cool. I mean, it's pretty cool for a lot of reasons, right? Uh, the two that sort of come to mind right away, right, is number one, um, if we ever decide to like establish some kind of presence on the moon, we're going to need water, right? We're going to need water for ourselves, right? We can also use water as fuel. Uh, so yeah, very very cool. But the other thing that I like to think about is how did it get there? Why is it there? Why is it here in such large abundance and not here or here, right? So, but it's very very cool. And what I would like to do, and this live stream is just sort of following our noses here. So I'd like to here we go. The findings were published in the Proceedings of the National Academy of Sciences on August 20th, 2018. So let's go to the Proceedings of the National Academy of Sciences and see if we can actually find this paper, because these press release things are fine, but for me, I need more. PNAS. All right, getting closer. Let's see. Let's go to articles, maybe current articles. Let's see if we can find it here. There's going to be lots of other things, which is cool. I've never actually really looked at this publication. We probably should. I mean, there's all kinds of science here. Jump to physical sciences, applied physical sciences, pre-ordering of water is not needed for ice wrecking. No, that's not it. It's close. Chemistry, planetary sciences, tearing of any man, physics, statistics. I'm not seeing it here. What's the? Let's. We're gonna have to go back to it. Oh nope, I guess not. It was right here. What's this dude's name? Let's do this. Let's just do a search like that. Paste. Oh, not finding. Not finding anyone there. I definitely like to dig, so let's really try to find this sucker. if we can. Front Matter, Journal Club. New research in physical sciences, astronomy. Maybe is it now? I don't know. Would you call this astronomy or planetary science? I would call it planetary science, but let's look in astronomy. Oh, this is all published. Yeah, see, this is the only one that was published today in astronomy. So let's look in planetary sciences, because they said it was published today. Ah, there we go. Direct evidence. Okay, now. Oh, look. There's a little thing that says open access. Yeehaw! One of my big gripes. Okay, and I'll sort of back up and explain this. Okay, when scientists publish their papers, right? They can put in years and years and years and years of work, right? And then they publish their papers. Well, in order to publish, you have to pay the publisher to, print your paper, right? And it's expensive. It can be, hundreds or thousands of dollars per page, right? I mean, back um, um, back when I was actually publishing papers in the 90s, right? To get a paper into the Astrophysical Journal, I believe it was $500 a page. Okay. Now it's probably more now, right? I'm not quite sure if PNAS, I'm not sure if they charge that or not, but my guess is that they probably do. It's probably really, really expensive. But then what they do on top of that, right, for the most part, is if you want to read their papers online, you have to buy them. You have to buy them, and they're like, $30, $40, $50 to read the stupid paper. And it's like, but you guys have already been paid for it. Anyway, so that's just a gripe. So let's look at the actual paper. Yay. I'm actually going to grab it and save it because you never know. um, okay, so let's, so here's the actual paper. This is the scientific paper, and this is the stuff that I am mostly interested in. So this first part here, it's called an abstract, and it's sort of like a executive summary of the entire paper, right? So water ice may be allowed to accumulate in permanently shaded regions on airless bodies in the inner solar system, such as Mercury, the Moon, and Ceres. Unlike Mercury and Ceres, direct evidence for water ice exposed at the lunar surface has remained elusive. Right. So they have actually found water ice on Mercury and on the asteroid Ceres, but they've never, I guess, found direct evidence for ice on the Moon. So we utilize indirect lighting in regions of permanent shadow to report the detection of diagnostic near-infrared absorption features of water ice in reflectance spectra acquired by the Moon mineralogy mapper instrument. Several thousand pixels with signatures of water ice at the optical surface are identified within 20 degrees latitude. Okay, so that's sort of what I thought, is that this is probably 10 degrees and this is 20 degrees, right? So we're just seeing the extreme southern part. Can we let's just to give you a perspective here, and this is going to be sort of an approximation, but let's I can do a pretty good approximation of that. Doesn't particularly matter. This one's good. Okay, so this is the South Pole, right? And here's the North Pole. And from the North Pole to the equator is 90 degrees, right? So this is 90. So half of that is 45. And then half of that again is like 22 and a half. So somewhere around here is about 20 degrees north, right? And actually, I should flip that around, right? The equator is usually called 0 degrees. So it goes from 0 to 90 and then 0 to negative 90. So this would be what, plus 70 degrees north. So right around here, and then again down here in the south, right? So it's just this extreme southern portion. We can actually try to identify some craters. Let's try to identify that big crater on the north. Can we do that? Yeah, maybe not. It might be on the other side. Yeah, that might be difficult to do. I'll give it one more try. Yeah, I'm not really seeing it very well. All right. Well, anyway, let's keep going here. So 20 degrees of both poles. Most ice locations also exhibit lunar orbiter laser altimeter reflectance values, and also the Lyman Alpha mapping project instrument, UV. So this is all done with spectroscopy, right? They're actually looking at the light coming from the surface, and they're running it through a spectrometer, spreading the light out, and looking for either like the absorption lines or some kind of emission lines that say that is water. So very cool. What else we got here? Okay, so here, these are spectra, right? These are different spectra. You can see the wavelength of light here goes from 1 micron out to 2.5. So this is definitely towards the infrared, right? We can't see this. We see light in visible, which is shorter than that. But let's see if we can make some heads or tails out of this thing. I'm going to back this up a little bit because this is a big plot. So reflectance spectra of ice-bearing pixels in red and non-ice-bearing pixels in black. Okay, I see. So a pixel with no ice looks like that, and a pixel with ice looks like that. And yeah, I mean, as you can see, there are differences, right? A place where there's no ice, you sort of get this peak thing here. It goes up, right? But where you get a place with ice, you actually get this dip, right? Same thing here, right? There's a dip here, but there seems to be a rise here. Yeah, so it's hard to interpret all these things, but yeah, and it is just a bunch of wiggly lines, but all those wiggly lines, especially these dips here, and the rises here, that tells us things about what is there, what is making up the composition of that particular place on um, um, on the moon. Oh, and here's a spectrum of pure ice frost, right? Oh, okay. See, so this is great, right? Because this is what, it sort of should look like, right? And this is what it actually does look like. So, wow, uh, that's a pretty good match, right? You've got highs here, all these highs, sort of all these lows. Here's a low here. So, very cool. Very cool. Interesting. Pretty interesting. Uh, Spectra are extremely hard to understand, and even harder to interpret. Uh, um, if you're not understanding a lot of this, that's okay. You'll get it. You'll get it eventually. Um, you know, keep looking at these kinds of things. Read the captions. That's always a good place to start, and you know see if any of it makes sense at all. Some of it will, some of it won't. Um, what you have to do in science in general is you really have to stick to things because believe me, speaking as a scientist, you don't understand things right away. You have to look at them and look at them and look and look and look and try to figure out what does that mean, you know, all of that, right? So it's not as if scientists, really have that much of an understanding at first either, right? It's just over time, thousands and thousands and thousands of hours of staring at this kind of stuff, where you start to get familiar, you start to see patterns. It's like, I mean, if this is what ice should look like, then it's like, wow, that's a pretty good match. It's not bad. It's not exact, right? And that could be for lots of reasons, right? Maybe the instrumentation isn't quite right. Maybe it's not pure water ice, right? There might be dirt in it. There might be other stuff in it. Who knows, right? So, anything is going to change these, but that's not bad. You have sort of all the bumps in the right places and all the holes in the right places. Not bad. Not bad. Just looking at this, it's like, yeah, I think they got a match. Pretty cool.
You're way behind the chat.
Am I way behind in the chat? Oh, well, you guys. Wow. Okay. Yeah. That's okay. You guys have a good time. You can listen to me too. So yeah, watch out for Patrick, man. You got a duck. Cheers. Okay, Daniel, I see you're mentioning in the chat that you posted a link to an article. Okay, cool. Let's what article is it? Okay, cool. Okay, excellent, excellent, excellent. Yeah, nice. Thanks. It's a link to this article. Excelente. Okay, so this is just more spectra. I guess I'm not going to get into it too much here. Let's see. Scientists, we like to do all kinds of of stats, and we like to make these kinds of plots to really show that what we're doing is right. That they're showing that they've done some kind of a full analysis, trying to take into account all kinds of stuff. Um, and I'm not going to get into this now. There's no point. But okay, here we go. Here's a annotated version of that lunar plot. So let's see. Distribution of water ice bearing pixels, green and cyan, northern and maximum temperature, albedo, right? Ice tends to be extremely reflective. I'm not quite sure what lamp is. We'll have to find out exactly what that is. So then they get into exactly how they did this, right? Their methods. So very cool. Of course, lots of references at the end. So yay. That's pretty nice. That's pretty nice. So, I mean, as I said, one of the things that this is saying is if we humans do want to establish a presence on the moon, right? We're probably going to have to go to either the North Pole or the South Pole, at least at first, and then maybe build some kind of infrastructure to pipe that water down to the more equatorial regions. So let me see if I can try to catch up with the chat. Yeah, sometimes I forget exactly where I am. Totally. Cool. Yeah, Mother Nature, any telescope is good. And in fact, to do astronomy, you don't even need a telescope, right? You don't even need binoculars. You don't need anything. You just need a pair of good eyes, and you don't really even need a dark sight. A dark sight is nice, but it's not really necessary, right? You can look at satellites. You can look at meteors. Most of the brighter stars you can actually see right in the middle of a city. So there's a lot that can be done uh, um, uh, without any kind of equipment at all. So very, very cool. Da, 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 yeah. Um, yeah. Well, the moon doesn't exactly have an atmosphere. I mean, not anything what what we'd consider like an atmosphere. It does it it does have a thin layer of very, very light and or gaseous material, but it's extremely thin, and you know usually not really even there. So technically speaking, it really doesn't have an atmosphere, but it sort of depends on how you look at it. Da, 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 da. Yeah, watch out for Patrick's duck farts. There, as I said, you just have to duck.
And I have to say, take care of Mother Nature and see if needs to get dinner for her daughters.
Cool. Yep. Take care. Thanks for coming in. Come on in.
You're still on though.
Yeah. Okay. Yeah. I'm just going to say this. Generally speaking, feel free to come in here anytime. I am here. We are here every single day at 2 hours UTC. So come on in anytime you want. If you want to come in each day, that's great. If you want to check in every week, every month, awesome. Whatever you like. Um, as I said, I'm here just to share the passion of astronomy, and yeah, I think it's great, great fun.
No problem, Mother Nature.
Mhm. You know, uh, uh, I've got, and in fact, I've had that song in my head all day long. The what's that song? It's the new Mother Nature coming over. It's the new Mother Nature coming. That one. Who does that? I forget who. It's oh, I forget. Anyway, I've had that song in my head all day long because of you, Mother Nature.
Yeah, she would love to connect and possibly do an interview to help get your channel out there.
Oh, that'd be cool. Yeah, I'm sort of behind in the chat, so let me catch up here a little bit.
And I usually call him Cosmic, but his name is actually Matt.
Yeah, it's Matt. Just don't call me late for dinner. That's it. Just don't do that. I forbid it. You can call me anything else. uh, let's see. Yes, Bob Dog. You normally you have to pay. You have to pay. Archive.org is nice enough to put the articles up for free. So most of the articles that I like to see are free.
My
But
name
if you
is
actually,
Bobby, Mother Nature. Bobby.
yeah. Uh, but if you go to the actual publisher, to their website, you usually have to pay. They ask you to pay, and that is ridiculous.
Out of bounds.
Yeah. Um, if you ever want or need an article, get a hold of me because I will. I have ways of getting them. Let's see. Now that it looks needs more pictures and graphs in the future. Uh, yeah, absolutely, absolutely.
Not a
Uh,
problem, Mother Nature.
I'm slowly catching up here. Yeah, spectral analysis is really hard. It's hard in general, but the thing about spectra is that it's so full of lots of information. It is just packed full that it's just absolutely amazing what you can get out of spectral information. You can get temperatures, you can get how much stuff is actually there, quantities, um, what stuff is there, uh, just on and on and on and on and on. So yeah, very cool. Um, blonde. Let's see. I'm slowly catching up to the chat. Oh, yeah. I saw a temperature of like 110K, which is really cold. That's 110 Kelvin. Um, let's see. Uh, I think 0 degrees Celsius is something like 273 degrees Kelvin, if I remember right. So yeah, it's cold. It's really, really cold. That is seriously icy ice. Solid, solid ice. Yeah. Mail, comment, Bobby, uh, Mother Nature. It's great to have Mother Nature in the chat. That's just awesome. Figuratively and literally. All right, well, cool. So ice on the moon, it looks like for sure. And up until now, we had never been really, really, really sure. And now it it looks like we are really, really sure. So very cool. Very cool. So the other thing that I wanted to share was, for some reason I'm sort of on a variable star kick. Um, and I found a paper over on archive.org today that talks about a variable star that's actually what's called a contact binary system. It's actually two stars that are so close to one another that they're in physical contact with one another, or at least that's what the models say, right? Now, whether they are or they aren't, we can definitely not say. We don't have the resolution in order to see the two stars. It's all that we're seeing is this light curve, right? It gets bright, it gets dark, it gets bright, it gets dark in some kind of periodic way. And it's the structure of that light curve, it's the shape of the light curve that we can take that data, feed it into a model, and say, okay, what is the best situation um, for these two stars that will make this light curve. So let's go over there. I'd posted that over on the Discord server. So I'm going to go over there and then I'll share my screen. Da-da-da-da. So now I'll share my screen. I'm going to hide that. Play with infinity for a while. Woo! There's Bobby. Look, he's going to infinity. Look at that. All the way down. I think this is really, really cool. I think most people don't like this, but I think it's very cool. I could play with that for hours. All right, but I won't. So yeah, here's what they're calling a contact binary star, and its name is MW Andromedae. So it's in the constellation of Andromeda. Well, let's go over to AAVSO, to that same database, and let's just sort of look and see what AAVSO has to say about it. We could actually look on Simbad too. There's just so many things to look at. Let's see, variable star index. Let's see if we can find it here. Come on. Let's sort of double play. We'll do Simbad and AVSO at the same time. Simbad is back. Yay. Let's do a search. And we're going to search for MW and search. Oh, there it is. Yay. Okay, let's do the same thing here. Yay, it's there too. It's a pretty faint star. I mean, in V, which is sort of, right in the middle of the visible range. It's magnitude 14, right? So with my telescope, just looking through it with my own eyes, I won't see that thing. No way. That's too faint. Now, with my camera on it, like a CCD camera, and a moderately long exposure, yeah, I'd be able to see that one. No problem. So let's see, what does AVSO say about this guy? So it looks like it has a period of like 6.3 hours, right? So it's really, really, really fast. I mean, these are two stars, right? Stars, did they say here? Yeah, they don't say here any kind of spectral type. Am I seeing a spectral type anywhere? Not seeing a spectral type here. They'll probably talk about that in the paper. Not really seeing a spectral type here either. Here's of course, an image of the field that has the star in it. Sort of back up here a little bit. Okay, yeah, it's just one of one of many stars, right? I mean, just sort of a nondescript star, but there it is. That's the one right there. Kind of cool. All right, well let's take a look at this paper here. So yeah, they did a lot of observations, right? Almost 1,300 observations of this thing. So they've got a lot of data, and it's, as I was saying yesterday or the day before, there's a lot of information that you can sort of infer from just the light curve, and they've definitely gotten into that a little bit. So these guys are over in Pakistan, right? At least a couple of them are. And one of them is at Tarleton State. I'm not quite sure where Tarleton State University is. Not quite sure, but I guess they have a 0.8 meter telescope. That's like a 32-inch telescope. And so they made observations of this system, whole bunch of data, lots and lots of data. So yeah, they share a common envelope, meaning that they're in contact with one another, which is pretty cool. Kind of interesting to think about. And they are zipping around one another, right? They are going around each other every 6.3 hours, right? So even in the amount of time that I've been live here, right? It's been almost an hour. They've gone 1/6 of the way around already. So pretty amazing. Pretty amazing. So here are the light curves that they made as a result of all their data. And I was looking at this before, so I kind of have a general idea of what they're doing. So you can sort of see this gray area here. That's actually a bunch of open circles, right? And that is their data, right? So this axis here is actually phase, right? So one phase is like one period, right? One revolution of these two stars. And what's this over here? Normalized intensity. So, and what they've done is they've looked at this system with three different filters: B, V, and R. So B is sort of blue, V is in the green, and R is pretty red. So it's definitely brightest in the blue and faintest in the red, right? But you can see that the light curves are pretty complicated, right? You've got dark, and then it brightens, and then it darkens again at about half phase, and then lightens again, and then darkens again. And what these guys have done is they've actually created a model showing the system itself, right? So this would be at phase 0, right? Where we have the um, um, the A component sort of face on, and the B component is actually behind it, right? So it's all we're seeing is just the A component, and that's what we're seeing here and here. In this case, it turns out that the B component is actually brighter than the A component, which is kind of unusual because, as you can see in their model, right, the B component is smaller. It's smaller, but it's brighter. So that's a little um, 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 oh, unusual, right? So as you move to quarter phase, it gets its brightest. And that's because we're actually seeing both of the stars at the same time, right? So all the light from both stars we're seeing, right? Then it goes into half phase, and that's this, right? Where some of the light from the larger component is being blocked, and we're mostly seeing light just from the B component. So as you can see, this isn't, this is still a darkening, but it isn't as dark as this. So then at 3/4 phase, brightens up again because you're seeing this. Now, these guys have even gone further in their models. They've actually put sunspots on these things, to see if they could match up the curves that way too. And as you can see, this black line here, that's their model. And yeah, it's a pretty good match. Even sort of, this flat area here, you can see it in the data. So pretty good. Pretty good. Okay, so the dashed line, you can sort of see a dashed line here in places. That is the solution with no sunspots at all. And the black line is with sunspots. And I sort of dare say that I'm sort of thinking that the one with spots is a pretty good match. Pretty good. So yeah, I just sort of wanted to show this off because they actually show, I mean, and this is just a model, right? This could be completely wrong, right? It could be totally wrong. But at least according to the model, right? They build this model and then they can make a light curve from this. And it's a pretty good match. So one can sort of infer that maybe this is what it looks like. And as you can see, they are in contact. They're, they're sharing a common envelope there. So pretty cool. Pretty cool, I thought. All right, well, awesome. Let me Let me stop sharing. Maybe check back with the chat really quick. Let's see, stop sharing. Go back over here. Anything else? Nope, haven't. No new activity. All right. Very, very good. Well, it's we are right on the hour. If nobody else has anything, maybe I will call it a little bit short, maybe a little bit on time tonight. What do you think?
Doesn't matter to me.
All right. Since Bobby doesn't care, yeah, I think let's get out of here. I mean, uh,
Did you listen to Horse in Space this week or no?
I recorded it and I listened to it, but it was I very very much had it way in the background, so I haven't really gotten a good chance to listen to it yet. So I like to listen to that kind of stuff with the headphones on, and not through any kind of speakers or anything. I like to have a good pair of
It is,
headphones
Uncle
on.
Bill.
Uncle Bill's in the chat. Ah, he is. Very cool. Nice to see you, Uncle Bill. All right. Well, water ice on the moon confirmed, and that is um, very very cool. We've been wondering about that for a really 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 long time because I mean if there isn't any sort of easy fuel on the moon, then it's going to be sort of a harder argument to want to go there and stay because we're going I mean we have to bring it all, right? But now that we know that there is, and I didn't we'd have to look in the paper to see if they were able to quantify like how much there actually was. um, let's do a quick, let's go back to that. Let's just do a quick scan and see if they have any kind of estimates in terms of how much water there actually is. Uh, let's see, we'll have to pull up the paper again here. I'm just going to do a quick scan, see if they give any indication as to how much. So yeah, maximum temperature below 110 Kelvin. So that's cold. Um, spectral modeling show that some ice-bearing pixels contain 30% by weight of ice, mixed with dirt. Yeah. Observation spectral features of H2O confirm that water ice is trapped and accumulates in permanently shattered regions of the moon. Some locations it's exposed on the modern optical surface. Okay. But I'm not seeing, at least in the abstract, any indication about if they were able to measure how much. So I'm just going to go through this really quick. And I'm looking for numbers, right? That's because they're going to be presenting that in terms of numbers. So I'm doing a quick number scan here to see if there's anything obvious. Should have looked before, but I didn't think of it. Patchy distribution. Okay, so each dot represents 280 by 280 meters. So that's a pretty large area. can't believe that they wouldn't have tried to quantify this. Not seeing anything there. And I'm going to have to zoom in on this a little bit. Two steps. Huh. I'm not seeing any quantities.
Womp, womp, womp.
Yeah.
Ah.
I wonder why they wouldn't try to quantify it. I mean, they have, I would think that they would have the data to do that. Huh. I would think that they would have enough data to do that.
Mm.
I'm doing another scan of numbers just to make sure because, you know, I miss things all the time. 70 to 90. I'm seeing wavelengths. Yeah, I'm not seeing any quantities here. I mean, just looking at the picture though, right? Let's just sort of make some guesses, right? So each one of these little dots, right? Each one of these little dots, right, is 280 by 280 meters, right? And there's a lot of dots there, right? Lots and lots of dots. Heck of a lot of dots. And this is just the north, right? The south, there's even more. All right, look at all that. So they did say, right, that at most it's like 30% water in those dots. If we knew how many dots, yeah, there's a lot of water. That's a lot. That's a heck of a lot. But I'd sure like to have a number. Yeah. All right. Well, I think now I'm going to get out of here. So I'm going to stop sharing that really, really cool map. And all right. Well, let's do this again tomorrow. How about that? A little less. Yeah. Yeah. A little less than 23 hours from now. One more spin on this tiny little planet. Yeah, let's do it again. So thanks for coming in, everybody. I will see you later. Bye.
Later.